Hello everyone, welcome to our next video. Today we will understand how the basic logic gates in the digital logic works. We have taken an AND gate. The two input pins are labeled as A and B, and the output pin has been labeled as Y. The truth table has been given here, where you can see the AND gate only gives a high output only when both of the inputs are high, else it will always give a low output. The basic notation is A dot B. So here you can see we have taken a simulation about how we can see or explain the timing diagram. You can open it from the simulation tab and clicking on the timing diagram window. So let's toggle our pins first. For input A as 0 and input B as 1. You can see the output has not been changed. For input pin 0 as B and input pin A as 1. You can again see the output still remains the same, but when we change it to high for both the pins, the output immediately changes to 1. Okay, so our next gate is OR gate. We'll take the pins for OR gate now. The truth table of OR gate states that the output is high when any one or both of the pins are at high state. The denotation is by A plus B. Changing pin B as 1, it becomes 1. Again, taking B as 0 and A as 1, the output again becomes high. When both are high, it again becomes 1. Moving towards our next gate, which is NOT gate. Here you can see the output will always the opposite of the input. The notation is complement of our input, and the truth table is when pin A is 0, the output pin Y will give 1 and vice versa. Now taking the pins for NOT gate, and toggling them, you can observe the timing diagram of both the pins. Next, we will see that of NAND gate. Here, you can observe it as the very opposite of AND gate, where in AND gate, we were seeing the output is high only when both of the inputs are at high state. But here, you can see when both of the inputs are at high state, the output is low. But when any one of the input pins or both of the input pins is low, the output is high. The basic notation for NAND gate is the complement of A dot B. Let's see the timing diagram to verify it. Taking A as 0 and B as 1, you can see our output is 1. Also, the timing diagram verifies it. Again, taking both as 1, our output becomes 0. When we take A pin, pin A as 1 and pin B as 0, it becomes 1 again. When both are 0, it is 1. But when both are 1, it becomes 0 again. Our next gate is NOR gate. When we add an NOT gate with OR gate, we get not NOR gate. So here the output also inverts, and as you can see, the output is high when any one or both of the pins are at high state, but it becomes 0 when both of the pins are at low state. In the truth table of NOR gate, you can see this, that when both of the pins are at low state, the output becomes high, but when any one or both of them are high, the output becomes low. The basic notation for NOR gate is complement of A plus B. Let's verify it. Taking pin A as 0 and pin B as 1, our output becomes 0. Again, taking both as 0, our output becomes 1. When we take pin A as 1 and pin B as 0, our output is 0. Here you can see the timing diagram matches with it. For both pin as 1, our output will be 0. Next is XOR gate. XOR gate is a very interesting gate. As you can see, the output is high only when both of the pins are at different states, maybe 0 and 1 or 1 and 0. When both of them are at same state, maybe high or low, the output is at low state. The basic notation is complement of A dot B plus A dot complement of B. Let's verify it. Adding the pins for the timing diagram. Taking pin A as 0 and pin B as 1, we get our output as 1. Again, taking both of them 1, we get our output at a low state. Taking 0 and 1, we get output as 1, or 1 and 0, we get output as 1, and 0 and 0 gives the output at low state 0. The symbol of XOR gate is a circle and a plus sign within it. Our last gate is NOR gate, XNOR. Let's add a probe to it. Let's label the probe as XNOR Y. So you can see the notation for XNOR gate is complement of A dot complement of B plus A dot B. Here it is the complete opposite of XOR gate, where at the same state when both pins are, we get the output at high voltage, but when both of the pins are at different states, our output is low. Let's verify it. So taking 0 and 1, we get 0. Again, when 1 and 1 at input, we get output as high. Again, when 1 and 0, we get 0, and 0 and 0 gives us a high voltage. This is the symbol of NOR gate, where a point between a circle is given to denote NOR gate. So this is for today. Thank you all for listening to this session.